Weather's a fantastic subject. When you think of it, when you meet someone for the very first time, what's the first thing you talk about? You know, it's an icebreaker, right? So it's nice knowing a little bit about the weather. Sometimes I meet people and I start talking about the weather and their eyes start glassing over and I know I've gone too far. So I dive it back in. So. Where's the mic? Where's the clicker for that?
Oh, I think it's on the podium there.
All right.
Yeah.
There we go. So again, my name is Bill Jameson. I've worked in the world of weather for over 35 years. Worked as an official weather observer for 37 years at different airports across Canada, mostly in the Maritimes. Greenwood with the military, Summerside with the military. When the base closed in Summerside, I was one of the first ones to leave the base when it closed because I accepted another job in Transport Canada doing the same thing. So since the base was closing, I was able to get out really, really fast. So they let me out. And then once I get into Transport Canada, I was stationed in St. John's, Newfoundland, and then finally shot down where I worked for about 31 years before finishing my career back in 2022. And I'm still in the weather, even though I'm retired. So. I worked as an aviation weather briefer, mostly for light aircraft. So they call up, whether they're flying from here to Moncton or here to Montreal, they call me and I'd give them a weather briefing for their flight, for their aviation. The two places I worked here in Charlottetown PEI were Summerside and Charlottetown. So I had the privilege to work in both airports. So if you ever listen to Jay at night, in this weather forecast, he says the weather observations from the Charlottetown airport. So for 31 years, I was one of the guys that put those weather reports out. So I do have a little bit of experience, although I'm not a meteorologist. I'm a weather briefer, weather presenter, weather observer. I'm an official weather observer. So my weather reports are gone down in history like as official weather reports. So it's great. So let's get into some weather. If you listen to Jay, he'll talk about computer models. Does anybody know what computer models are? Do you have any idea when Jay talks about computer models?
Do you mean the UK or
Mhm.
the
Yeah,
European
that's-
and
yeah,
the North American
yeah.
side?
So they're supercomputers. So a computer model is a massive software program that simulates the Earth's atmosphere to predict the future state of the weather. So instead of relying on a meteorologist's intuition or looking at historical weather patterns, these models use fundamental of laws of physics to calculate how air, moisture, energy move around the planet. Model inputs. So before a model can predict the future, it needs to know exactly what is happening right now. This is called data assimilation. So how it gets the weather into these computer models, satellite imagery, weather balloons. Weather balloons are released twice a day, all across the Earth. That's the same time every day. GMT time, it would be 12 Zulu and midnight Zulu. So a balloon goes up in PEI, or they don't do it here in Charlottetown, but the closest one here would be, I think, Jameson. And one would go up in Yarmouth, one would go up in Set Hills, one would go up in Sable Island, all around the world, Russia, Siberia. And as those balloons go up there, they're gathering data, and then they send the data back down to the ground station, and that feeds the computers. So the computer now has a snapshot of what the atmosphere is from the surface of the ground right up, right around the globe, right? So those are weather balloons, and they're issued twice a day. They also get data from commercial aircraft. You fly Air Canada, when Air Canada's flying at 35,000 feet, it's providing data to the computers. Temperature, wind direction, wind speed, et cetera, et cetera. Also from ocean buoys and ocean ships are also doing the same thing because there's no weather stations in the middle of the Pacific, but there's ships out there. So they're inputting data to these weather models as well. And finally, ground-based weather stations, which would be me working at Charlottetown Airport, as well as radar. So a lot of data is going into these computers. So they're supercomputers. Now the computers do its thing. Once the computer has assimilated all the data, it begins to crunch the numbers. And it usually takes 6 or 7 hours to crunch all the numbers. After it crunches the numbers, it comes out with the forecast. And the data is converted into visual maps, charts, and data feeds. Meteorologists then interpret these outputs to create the daily forecast. So Jay Scotland and all these other forecasters, they don't forecast the weather. The computers forecast the weather. They interpret the weather. And they decide whether the computer is wrong. All right? They say, I don't think it's going to be -5, and I think it's going to be -10. So they can change it. So they interpret it, and they massage the data a little bit. So we have some, these are some of the models that are out there. So the ECMWF is the European model. It's the king. When I say the king, it's the big guy. It's usually the one that's always right. And then we have the GFS, which is the American model. The GEM is the Canadian model, and then there's others, Japan, Switzerland. But when I do my thing on my blog, I'm basically looking at the European model, and I'm using some of the Canadian model as well, trying to try it. So, yeah, so those are the models. Think of a model as you're baking a cake with all the ingredients. If you're going to bake cake, you're going to bake a cake. It's not going to be the same cake, even though you're using the same ingredients. Same thing as the models, because they may interpret the data a little bit different. So at the end of the day, they come out with different forecasts. But usually the ECMWF, the European model, always comes out on top. So, any questions on that so far?
I have one there. They cut back the United States a lot on their balloons.
Yeah.
So how's that going to?
Budget cuts, they're de-staffing a lot of these sites that send up the weather balloons. So less data into the computer means less data, less accuracy.
So like, is there, international oversight in terms of like the collection of this data
No,
and distribution to it? Like everybody just kind of, it's like almost like open source software sort of thing, like where everybody just kind of participates?
No, how could I say it? Like NOAA, the North American Airspace, is in the States, and Canadian is the GM, Environment Canada. They're involved in the Canadian ones. NOAA is for the States, and I don't know who's involved for the Europeans, but their budget, like their computer is so much more powerful than the ones in the States. And now they're getting AI involved in it, which is really helping things out as well. It's making it even better. So yeah, there's budget cuts with the balloons, like you say, and so garbage in, garbage out. So we may be looking at decreased accuracy going forward because there's less data going into the models. So with that being said, the Canadian daily forecasts. So have you ever looked at the forecast? They generally put out 3 forecasts a day here in Canada, or at least during PEI. They put out one at 5:30 in the morning. That's based on previous balloon launches. That's based on the previous data crunching, which is at midnight Zulu. So by the time the forecast gets put out, it's based on a data input that was inputted over 12 hours ago. Right. The next one comes out at 11:30 in the morning. Well, there's no balloons, but all this one does is fine tune at 5:30. So if the 5:30 one came out and said no thunderstorms, all of a sudden some thunderstorms started developing. They may put out, well, they will put out the 11:30 forecast, but they may now include some thunderstorms in it. For any surprises that they didn't have in the 5:30 forecast. And then the late afternoon forecast comes out at 4:30, and that's based on the morning's data, so, which is about 10, 12 hours old. So they're always running behind, right? And of course, they always put out an amendment to any forecast, like if something happens. So those are the 2 main forecasts, 5:30 and 4:30, with the one in the middle, 11:30, is just to fine tune it for the day.
So where would you see that? You want to get the latest forecast?
from Environment Canada's website? Yeah. And it puts it right on there. All this information is all free on the internet, my golly. The study, the stuff that's available on the internet now is unbelievable. Now you can, oh, I do my own forecast. I don't bother looking at Environment Canada. I do my own. Because it's all available, free of charge. You just gotta know how to interpret.
And so the Windy app,
Yeah, that's the one I use.
so where you use that?
I use that quite a bit, yeah.
It's pretty cool.
Yeah.
And so would that be pulling data from?
The ECMWF. Well, you can put the other models on that.
Yeah,
Yeah.
and so you can choose your model?
You can choose your model you want to
Maybe
look
if you
at.
get the pro account or something?
I think it's on the free account, but you can choose your model that you want to look at. Yeah. Windy.com.
Yeah.
Windy.com. All right, so that's just a little basic on models. Any questions on the computer model? So when Jay says the Canadian model or the European model, this is what he's talking about, the models. All right, let's talk about some
We
physics.
got
What?
some questions down here.
Sorry.
What is the life cycle of the balloons? What becomes, what altitude do they go to? And
They usually go up, after about an hour, they burst because as they go up, they expand. And then they'll burst and then fall back.
Could you
to here.
repeat the questions too, please?
I'm sorry.
Some of us are half deaf.
Okay, I'm sorry. Can you hear me now?
Yep.
Okay. So the question was, what's the life cycle of one of those balloons? So when the balloon goes up, once it gets up to 60, 70,000 feet, it bursts. Because it gets to what size of the football field. And it comes down. And a lot of them are turned back into Environment Canada. But you could find them in the woods. It's a little radio box.
So they'll, balloons just measure a hole.
I'm sorry?
They probably go roughly straight up when they're.
Well, they'll go straight up and then they'll drift with the wind, yeah.
Okay.
And they usually go up to
So
about
then
40,
the
50, 60.
flyers go the other way, like KLM,
Yeah,
27,000 feet, they're going
Yeah.
across.
Yeah.
And-
They learn to recognize them. They learn to recognize them and they stay away from them. I don't think you can't miss them with the size of a football field up there. A big balloon going up there, right? So. And they go on weather models or the forecast times. So if you're looking for a forecast and it's 6 o'clock in the evening and you know that the forecast should have been out at 4:30 and the one that's been shown is 11:30 in the morning, it has not been updated. So you may as well wait for the new one because it'll be brand new data. So the one in the morning and the one in the evening or late afternoon, they're brand new data. So it's a brand new forecast based on brand new data. So if you wait for a snowstorm to approach and they're saying 15 to 20 centimeters at 10 o'clock in the morning, wait to the 4:30 forecast to come out because that's based on brand new data. And then they come out with 40 centimeters. Because they got new data to work with. They got new data. All right, so let's get into some, a little bit of physics here. So air masses. Does anybody know what an air mass is? Have you heard Jay or anybody talk about an air mass? So an air mass is a large section of the atmosphere with uniform properties of temperature and moisture. It's like an upside down cereal bowl. And it has the same properties of temperature and moisture in the horizontal. So from here to Montreal, if it's minus 10 in Charlottetown, it's probably minus 10 in Montreal. It's the same. It's the same. So think of this as an upside down cereal bowl. It develops when air lies stagnant over a source area for a long time. So think of the tundra, the North Pole. And air sits over that, it's gonna get cold. Once it forms, it starts to drift out of that area. So once formed, the air mass starts to move away from that area. That's why we can get minus 25 in Charlottetown. Because that air mass formed in Russia or Siberia or and it moves south. And in wintertime, the ground is covered in snow. All the lakes are covered in ice. So it doesn't get a chance to modify or warm up. So when it comes south, it stays cold and dry. and right down into, New York State, because it stays cold. So that's air masses. On the other hand, we can get an air mass that comes up from the south and be warm. Next day it's 10 degrees, rain, but it's 10, it's a different air mass. So again, think of the Arctic in winter, it's cold and dry air mass. If the air mass developed over the desert, it would be hot and dry. If it developed over the tropical Atlantic, it would be hot and moist. So that's different air masses. Each air mass has different weather associated. So when that air mass moves over your house or over your location, you're going to get the same weather associated. Weather fronts. Everybody's heard of weather fronts before. Cold front. Anybody name some more fronts? Warm front. Weather front. So air masses don't generally mix together. It's like oil and water, right? So fronts are narrow transition zones between, it should be two different air masses, not three, two. So think of a house, a one-story house. Each room is an air mass. Well, there's walls dividing those rooms. So the walls would be the fronts that is dividing the air masses. And the fronts is where the battleground is. The fronts are the battlegrounds where all the weather happens, where a lot of the weather happens. So a cold front is the leading edge of an advancing cold air mass. So if you hear me saying on my blog, there's a cold front coming, or Jay saying, there's a cold front coming, there's cold air coming. The mailman brings the mail, cold front brings the cold. Warm front will be the leading edge of an advancing warm air mass. So it's minus 10 in the middle of winter, minus 15, minus 20, and you hear them say that there's a warm front coming. Well, then you can know probably the next day it's going to get warmer. Yeah?
What do they mean when you talk about a polar vortex?
I was hoping someone would mention that. Can we wait to the end of this? Just remind me. I'll talk about the polar vortex when we get to the end. It's a big thing in itself. So. Any questions on the fronts?
Why is photography always better after a cold front has gone through?
Why is the what?
Photography.
Oh, because the air is clear. There's less haze, less dust, less moisture in the air. So the air is clear. I'm sorry, she asked, why is photography better behind a cold front? Because it's a different air mass, and generally cold air is clear. And so it's nice. So you don't get the interference or on the camera lens. Water vapor. What's water vapor? Anybody know what water vapor is? Can anybody tell me what water vapor is? Have you heard of water vapor before?
Oh, yeah. An illness where you have to lie down.
Water vapor is an invisible gas. So there's water vapor in this room right now. You don't see it. And this is the most important gas found in the atmosphere. So water vapor is the most important gas found in the atmosphere because it has the ability to change state under normal conditions. So water vapor can condense into visible water droplets, clouds, right? Raindrops, drizzle drops. And then those clouds, the raindrops can freeze into snow. So water vapor is a gas, it's water vapor. Water is a liquid, it's water droplets. Water is a solid, it's ice and snow. So what would a cloud be? A vapor, droplets, or ice and snow?
Droplets.
What's that?
I think you're on all three.
So a cloud, is it invisible? So water vapor is invisible. If you can see it, it's not a gas. So there's water vapor in this room, we just don't see it. We can feel it, but we don't see it. If there was a cloud in here, then it would be water droplets. Small little water droplets. Fog, think of fog. And water is a solid, will be ice and snow. Anybody heard the reference dew point before?
Yes.
Dew point, very important. So we can say that the temperature outside is 25 with a dew point of 20. So what does a dew point of 20 mean?
That you almost have fog.
Almost at 5? Define almost.
Well, if it were the same as the dew point, you would have fog.
Yeah. So the dew point temperature is the temperature at which the air must be cooled in order for clouds to form. So if the air temperature is 25 and the dew point is 15, the air temperature has to cool down to 15 degrees before we're going to get any fog. Right? Or we can raise the dew point temperature to the air temperature by adding moisture to the air. Evaporation from a pond or a lake, you can add water to the air through evaporation. That way we can increase the dew point to the air temperature, and then we can get fog forming. So anytime the temperature and the dew point are really close together, it's really humid. So like in the summertime, when you get those hot humid days, the temperature is 25 and the dew point is 21, you're sweating buckets, just sitting there sweating buckets. But the dew point was 4, temperature 25 and the dew point was 4. You'd be dry as in, you would cut the grass, run marathons, you wouldn't sweat because it's so dry. So the closer those two temperatures are together, the more humid the air is. And the reason why they're important is because that's what drives clouds. As air rises in the atmosphere, it cools. Once it cools to its dew point temperature. And we have clouds form. Right?
When you have fog sometimes, and miniature drops of moisture in it, you get wet from it.
Yeah.
What's taking place there? I forgot what happened.
So she asked about fog and the small water droplets. So that could be drizzle in the fog.
Oh, yes.
It could be small. Or the cloud, or those droplets could bang together and get big enough, just enough to make you wet. Normally when it's drizzling, you don't see the water droplets on the puddles.
No.
Once you start seeing the droplets on the puddles, and then we call it rain showers or rain. As long as you don't see the droplets on the puddles and like you can see it in the air, we call it generally drizzle. Right? So the dew point temperature is really, really important because it tells you when the clouds are going to form or how high the clouds are going to form. If there's going to be fog forming in the morning or whatever. Right? So as a pilot, I'm a pilot myself, if you want to go flying, we're always critical about watching the air temperature and the dew point. Because if you're up flying and the temperature is 25 or the dew point is 15, that's great, no clouds, no fog. But as soon as the temperature starts dropping off, so the temperature was 25, the dew point was 15, the temperature starts cooling off in the evening, 20, 19, 18. The dew point temperature doesn't move, it stays the same. But once the temperature drops back to the dew point, then we're going to get some fog forming, so you have to be careful.
So when you're flying then, it depends on what elevation you're flying above the earth. If you're up 30,000 feet,
Yeah.
it's going to be different. Different elevations will have different breed areas.
Yeah, that's right. Yeah. Different layers. Was there another question there? Go ahead. How do you measure the dew point? The dew point is measured. It's all done electronically now, but in the old days we used to have a thermometer and we used to dip it in water. The bulb in water in wintertime, and then spin it to get an ice coating on the bulb. And then with the ice coating on the bulb, it'll give you a different temperature. So you have two thermometers. You have one with a regular air temperature, and you have the second one with ice coating on it, or wet, or you dip it in water, and as that water evaporates, it would give you a different temperature, so that would give you your dew point. Okay, so it's called a wet bulb. So you have a dry bulb, which is your actual air temperature, and then a wet bulb temperature. You use both of them together to come up with your dew point temperature.
How would the pollution or smoke affect all that?
Doesn't, how does smoke or pollution affect it? It doesn't affect it, no.
So a neighbor
I've seen those. That's atmospheric pressure, and we'll win it right in a little bit.
And it actually worked,
Yeah, I know, it does, yeah. We'll talk about that in a little bit.
but he had a feather in his bow, I don't know what.
Yes?
We can't hear the question, so if you could repeat it would be helpful.
She asked about those little toys, or not toys, they're little, like a duck with fluid in it. And sometimes when you're pressured, when there's a storm coming, the fluid will come out the beak or something. Is that what you're talking about?
No, there'll be a glass and a dip into the seat would dip into the water.
I think it's going to be about the same thing. It'll be because of atmospheric pressure. So the dew point is very, very important when it comes to weather. So the temperature and the dew point. So have a look at that when you're looking at the weather observations from the airport. It'll say temperature, dew point. It'll show you how close you are or how humidity. So there will be a temperature of 25 and a dew point of 15. That'd be a comfortable day in the summertime. So with the dew point, we also have what we call relative humidity. So the relative humidity is just a ratio of the amount of water vapor or gas that's in the air right now to the maximum amount of water vapor the air can hold at that temperature. So it's expressed as a percentage, 50%, 80%. So think of it as like this room is probably 21 degrees in here, 20 degrees. So right now at 20 degrees, the air can only hold, I'm just gonna say buckets, 5 buckets of water vapor. But if the air was 25, it could probably hold 10 buckets of water because it's warmer. If the air temperature was 10, it may only be able to hold 1 bucket of water. So the warmer the air is, the more water vapor it can hold. So if right in this room, let's say it's 20 degrees and the air is holding half the amount it can hold. Say at 20 degrees, the air can hold 5 buckets of water, but it's only holding 2.5 buckets. Well, it's 50% relative humidity. So that's how we call that. If the air was holding 75% of the water it can hold at that, then the relative humidity is 75%. And that's why when you sweat for a reason, because when the water evaporates off your skin, it cools you down. But when the air is very moist and the relative humidity is high, you don't sweat. Or you do sweat, but it doesn't evaporate off your skin to cool you down. So you stay wet and you don't cool off. But if you had a relative humidity of say 30%, you wouldn't be sweating at all because it would be evaporating off you as soon as it forms. So that's relative humidity. So relative humidity and dew point are almost the same thing. So the warmer the air, the more water vapor that the air can hold. Cold air feels so dry. Have you ever noticed that in the middle of winter when it's cold, your lips chap? Because the air is so cold, it can hold very little moisture. The desert of Antarctica, they call it a desert because it's one of the driest places on Earth. Because the air is so cold, there's so little moisture there. It hardly ever snows in Antarctica. But when it does snow, it doesn't evaporate it. That's why it builds up. Now we're going to get into talk about clouds. So clouds are formed when the air temperature and their dew point are the same. Fog is a cloud whose base is on the ground. So fog is a cloud, except it formed on the surface of the earth. If it formed at 500 feet, well then we call it a cloud. You can drive into that cloud if you go over a hill. And you can actually drive into that cloud, right? But you call it fog then. So clouds are a direct result of condensation of water vapor to visible water droplets. Condensation from water vapor to visible water droplets. You've ever noticed when you take a shower, the mirror is all wet because the water vapor in the air is touching the cold mirror and it's fogging it up. But if that mirror wasn't there and it cooled down, and then your whole bathroom would be foggy. Right? So if condensation occurs at the ground level, then it's a result, and the result is fog. If it occurs up in the atmosphere, well then we call it clouds. And there are several different types of clouds. We have some beautiful clouds out there. Did anybody ever notice, look at the clouds today? Pretty impressive, right? Some thunderstorm clouds. So we have four different types. First of all, we have low clouds. They're formed between the ground level or just above the ground, because if they're up the ground, we call fog. Just above the ground to about 6,500 feet. We call those low clouds. Can anybody give me an example of low clouds, if they've heard?
Cumulus.
It's a low cloud, but it's, so cumulus is a low cloud, but it's a different type. So we have stratus, stratus, yeah. Stratocumulus. Then we have middle clouds. They're found in the atmosphere from 6,500 feet to about 18,000 feet. And they would be altocumulus, altostratus, nimbostratus, various stuff. Then we have high clouds. They're from 18,000 feet and above. And they're mostly cirrus, cirrostratus, cirrocumulus. So low clouds would be mostly formed of water droplets and ice crystals. Because if it was in the wintertime, it'd be full of snow. Middle clouds can be formed of ice crystals or water droplets. And then the high clouds are generally ice crystals because it's so cold up there. It's all snow. When I call ice crystals, I mean snow or vice versa. And then the final one today is the clouds of vertical development. Those are like towers, cotton balls, and cauliflower. Those are the ones we had today. Did anybody see them? Yeah. So those were formed because of vertical development. Those other three types, middle, high, and low, they're layer type clouds. They form in layers, like a blanket. But clouds of vertical development, they form vertically. And they give you your showers. Wait a minute, and the cloud moves over, and then the sun comes back out again. So clouds of vertical development will give you your showers, your thunder showers, your snow showers in the wintertime. Your other clouds, especially your middle clouds, will give you your continuous precipitation, like continuous rain, continuous snow. But if they're calling for showers and thunder showers, off and on. Your neighbor will get rain, but you don't, type of thing. Atmospheric pressure. Anybody heard of that? I'm pretty sure they have. So the official definition of atmospheric pressure is the force per unit area exerted by the atmosphere at that level, or the weight of the overlying air. So if I had a barometer here, a barometer measures atmospheric pressure. If I went into an airplane and took that barometer up in the sky, it would measure less pressure because there's less air above you pressing down. It's gravity. So the higher you are, the less atmospheric pressure there is. The higher you go, the lower the pressure. The lower you go, the higher the pressure. Yes?
I'm just wondering, the barometers that you see in people's kitchens, do they actually give like an accurate reading?
Yeah. If they're set right, yeah. So he was asking about the barometers in your family room or your kitchen. Well, the ones with the dial, yeah, they're pretty accurate if they're set right, yeah.
You know when it's raining, and the clouds are really black,
Yeah.
why are the raindrops so much bigger?
So why are the raindrops so much bigger
Like this
when,
afternoon when I was up driving,
yeah?
massively raindrops.
Because what type of cloud was it?
It's a big black one right over there.
So it was a big black cloud vertically developed, right? Which means it had lots of depth for that, right? So that raindrop doesn't just fall from 1,000 feet. That raindrop could fall from, it probably fell as snow at 15, 20,000 feet, and it came down through. As it falls down, it collides with other raindrops. It's bigger and bigger, and then you get those big raindrops. Yeah, so the bigger the cloud, the thicker it is. When I say thicker, I mean height-wise. Usually the heavier the precipitation can be. That's why you get the thunderstorms. You can get those really heavy rain, because those clouds could be 60,000 feet thick at times. Yeah, really, really big. Yeah. Okay, so the atmospheric pressure is measured by barometers. It's recorded as millibars, inches of mercury, or kilopascals. I like the word millibars myself. But if you have your home barometer, it'll probably read inches of mercury, 29.47, 2989. That's inches of mercury. Millibars, I like the word millibars myself. So ground weather stations record the atmospheric pressure as part of their hourly weather report. So when I worked at the airport, we would put a weather report out every hour on the hour. And it would include all the clouds, the heights, the wind speed, wind direction, temperature, dew point, atmospheric pressure. So we have on a weather chart, we have lines that are drawn on a weather chart that are joining places of equal atmospheric pressure. Because now the meteorologists or the weathermen, they want to analyze these charts so they can make the weather charts. So think of atmospheric pressure as the chart as a topographical map. So on the topo map, the lines on the topo map measure what? Elevation. And what do they depict? Mountains, plateaus, valleys, etc., etc. What happens if those lines on the top of the chart are really close together? Steeper. So now let's switch that topograph over to a weather map. So now their lines are called isobars, and they measure points of equal, instead of equal height or elevation, they're going to measure same mean sea level pressure. And they would depict areas of high and low pressure, troughs, and ridges. So a high pressure area would be similar to a mountain on a topographical map. A low pressure area would be like a valley. And troughs and ridges would be like a ridge, a mountain ridge in a valley. The closer the lines are on your weather map, if it was a topograph, if it was a topo map, it would be steepness. So the closer the lines are, means there's a big pressure change in a short period of time. So we call it pressure gradient. If we have a big pressure gradient, we have strong winds. So lots of times you'll hear Jay saying, oh, the pressure gradient's going to increase. All he's saying is the lines are getting closer together, or the pressure change between point A and point B is getting, the gradient's getting bigger, so the wind is going to get windier.
So what causes the pressure to change? They're at the same elevation, standing there, so we explain what's changing over your head.
Because these mountains, they're not stagnant, they move.
So you have more air on top.
So think of a topo map. So the question was, what would make an atmosphere, what would make the pressure change? So if you were on a topo map and you were at an elevation of 100 feet, and you looked to your west and there was a mountain back there, if that mountain started to move towards you, you're going to start to climb as that mountain approaches, right? It's like driving to the Rockies. You rise up, right? So as that mountain comes closer, your elevation is going to go up. So same thing as a high pressure and low pressure area. You're sitting still, but the weather systems are moving all around all the time. They're moving toward you. And as they move toward you, your pressure is going to change. If the high pressure is coming toward you, your atmospheric pressure is going to go up. If low pressure is coming toward you, then your pressure is going to go down.
So what am I watching for? Sudden change in barometric pressure?
I'm going to get that in just a second. Yeah, I'm going to try to put it all together in a little short little bundle here for you. Okay, so high pressure. So the areas on the weather map with the highest pressure in the center. So if it was a topographical map, it would be the mountain peak would be in the center. So an area high pressure, it's in the center with the highest pressure, and it's usually marked by a large H on the weather map. And if it was a color chart, it would be blue H. Winds blow counterclockwise around the high. Have you ever had your tire blow out, or you tried to put air in your tire? What happens when you push that little valve? Psst, what's happening? Pressure in that tire is high. High pressure. As soon as you let it out, so what's the pressure trying to do? It's trying to go from high pressure to low pressure. So when you have a high pressure area, the wind tries to go to high to a low to equalize it, because that's an unbalanced state. So it tries to go from the high to the low. So now you have wind blowing from a high to a low. But due to the rotation of the earth, that wind gets deflected to the right. So now you have winds that are going to blow clockwise around an area of high pressure, an area of low pressure, they're going to blow counterclockwise. Because air is trying to blow into the low pressure system, but because of the rotation of the earth, called Coriolis force, it gets deflected to the right. So the wind blows clockwise around high, counterclockwise around low. So in Canada, most of our weather goes from west to east, is that correct?
Yeah.
West to east. What would be our good wind direction? What would be a good wind direction?
So,
When a storm is coming, what generally is the wind direction? Southeast, east,
depends on the season.
right? So if you put your back to the wind, stick out your left hand, you're pointing at the low pressure system. So if the storm track is generally from west to east or southwest to northeast, like nor'easters do when they come up from Cape Hatteras, put your back to the wind, which is usually out of the east or northeast, stick out your left hand, where are you pointing? Right to the storm. Right? Usually when the storm goes by, where's the wind direction from? West? Put your back to the wind, stick out your left hand. Now you're pointing to the northeast toward Newfoundland. The storm's already gone by, and it's moving away. So a southeast wind followed by falling pressure will normally indicate that you've got a system coming, approaching. And then you combine it with clouds approaching, thickening up, and you can do your own forecast. And you can, don't need Jay. Who needs Jay? Huh? I don't know, Jay. I'm harping on him. I don't know. If anybody knows Jay, don't say, don't He's fun, though. He's fun, because I criticize him at home. The wife can't watch the weather with me. She lives in another room, because I'm criticizing so much. So on a high pressure system, it's marked, on a weather map, it's marked with a large H. And it's usually associated with sunny, dry weather. I didn't say warm, I said sunny and dry, because we can get high pressure systems in the wintertime, but it's cold, it's minus 30, but you're under a big ridge of high pressure. But it's usually clear, sunny and dry. Now the opposite is low pressure. It's areas on the weather associated with, areas on the weather map with the lowest pressure at the center. It's marked with an L. Weather is usually cloudy and rainy. Wind blows counterclockwise around an area of low pressure. Clockwise around high, counterclockwise around the low pressure system. So there's a weather map. You see PEI? Can you see PEI there on the East Coast?
No.
I look at these all the time, I know exactly what I mean. See the big L there with the number 995 in it? Just look to the north and to a little bit to the left, you'll see the marathons. All right? So that would be like, that would be a low pressure system there. The black lines are called isobars. They're joining places of equal pressure. And the lowest pressure is in the center there at 995. Now if you look to the west over Ontario, you can see an area of high pressure. And it's at 1,023 millibar. But can you see just south of the Maritimes there, see how tightly those isobars are packed together? Very windy. Look over in Ontario, how far apart those isobars are. Not windy at all. And by looking at that, I can tell you what direction the wind is anywhere on that map. Because we said the wind blows counterclockwise around an area of low pressure. So over Cape Breton, what direction do you think the wind is blowing?
East.
East, exactly. Put your back to the wind, east. Stick out your left hand, where are you pointing? Right at that storm center. To the south. Sable Island, yeah. Now, these systems don't stay put. They're always moving. Generally in Canada, they go from west to east, but it's not out, because they could go from northwest to southeast, or southwest to northeast. Just generally west to east. But in the wintertime, you generally see the nor'easters, they develop down over Cape Hatteras, and they come up the coast, around Sable Island. And so if that was the case, if this was January, and that storm was sitting right there, I'd have the snowblower all formed up. These are the type of weather maps I'd like to see on Jay's forecast. But what do we see on Jay's forecast? We see a picture with an icon of a sun. What information does that give you? What does that give you? Nothing. Doesn't tell you nothing. But when you look at this, you can see where all the areas of low pressure are. You can see where all the areas of high pressure. You can see the associated weather fronts. They're the big black lines with the semicircles and the triangles on them. Those are the frontal systems associated. But I know this will be getting complicated, but you can just look at that one map. And if you look at that as a topographical map, think of the H's in Ontario as mountains, and the low over Sable Island is a big valley. It gives you a better idea of what's going on there. And that was probably from just a couple of days ago. Remember we had those parade of weather systems that was going by, kept us cloudy and cold for the middle of the week. That was just one of the storms that went by. It came down out of Ontario and Quebec, dipped down on Cape Cod, made the corner, and then went back up toward Newfoundland. There was about 4 of them that did that. Yes?
Sometimes when you hear a hurricane coming from the south,
Right?
it will either bring rain to you.
Right?
Is that coming counterclockwise from the water?
So a hurricane,
And then it goes the other way, you don't get the rain, you get the winds? Is that
so she's talking about a hurricane, about the difference in the weather associated with a hurricane. Generally, when the hurricanes come up to the Maritimes, they transition from a hurricane to an extratropical storm. And when that happens, they can actually become more dangerous because the wind field actually expands. In a hurricane, the wind fields are very tight. It's very strong, but it's very tight. It can only be maybe 20, 30 miles across of the very strongest winds. And once you get 40, 50, 60 miles from the center, it's, it could be 20-mile-an-hour winds. The strongest winds are right close to the center. But as the storms come up the coast and they become extratropical, the wind field expands. So now instead of having a 20-mile area with 70-mile-an-hour winds, we can have a 100-mile area with those strong winds. And generally, the windiest part goes to the left side, and the rainiest part goes to the right side of the storm track. So if the storm was going to go up, say the Bay of Fundy, most of the rain would probably fall over Cape Breton in Nova Scotia, and then it'd be windier on the other side. So, but hurricanes, when they're transitioning, no one knows, they can do anything. Because there's so much energy built into that one little area, the system has to do something. It has to disperse all that energy. Computer models, and they try. So, in Ontario, what type of weather would be associated with in Ontario there? Sunny. Light winds? Hardly any winds there. What about Sable Island? Yeah, they're in the middle of it. So they're getting rain and probably some fairly strong winds, 50, 60, 70 kilometer winds. So again, you know, you can look, if you look at, say, Manitoba, Winnipeg,
So,
what wind direction would be okay, no, let's go a little bit further west, Saskatchewan. What's the wind direction? So they generally follow the isobars. It generally follows, the wind generally follows the contour of the isobars. Southeast. Look at that, you can look at a weather map and you can figure where the rain is, the cloud, and you can figure what the wind direction is. These are the weather maps, I wish they put out on the.
Further out west, why are these atmospheric rivers happening in BC?
Oh, yeah.
All of a sudden, like, we've never heard of that.
Well, she was wondering why atmospheric rivers happen all of a sudden.
And suddenly, almost every year, they have at least one of these atmospheric rivers. Last
Well, maybe they were happening all these times, but we just didn't identify them as atmospheric rivers, and now we're only putting one and one together. We're seeing more observations, and with the internet, people are becoming more and more aware of it all the time. So I would say these atmospheric rivers were happening all the time, but it's now becoming, it's more visual, you can see it more. And it's much more effective because you have so many more people living in affected areas that are associated with these atmospheric rivers. And the weather's changing. The weather, you know, with the climate change, right? All right, so that was just a little bit about some basic weather, about temperature, dew point, you know, how fog forms, how clouds form, low pressure systems, high pressure systems, how winds rotate or spin around an area of high pressure, area of low pressure. You can watch these systems move by watching the wind direction. So if you get up in the morning and the wind is from the southeast, you know there's a storm coming. And the pressure is falling on your barometer. That means, you know, the wind is telling you there's something coming. Your pressure is falling. It's telling you there's something coming. The clouds are thickening up. Tells you there's something coming. And then all of a sudden the wind starts shifting around to the southwest, west, northwest. Once the wind gets around to the northwest, you can probably say, well, we're coming around to the end of this. It's gonna clear, not clear up, it may stay cloudy, but the rain and the snow is probably gone. So you can do your own short-term forecasting by just knowing a little bit of basic meteorology. So.
You were gonna mention more about polar vortex?
Okay, polar vortex. We've all heard of polar vortex, right? Is it evil?
Yeah.
No, polar vortex is not evil. Has anybody ever seen a spinning top of a child's toy where you push down and it spins on a little thimble?
Yeah.
All right. So over at both poles, North Pole and South Pole, we up high in the atmosphere, I don't know how many miles, 40, 30, 50 miles up. The air is rotating fast, like a fast jet stream. It's going all the way around, say the circle, Arctic Circle, and the Antarctic Circle, high up. And what that does, that keeps the cold air bottled up in the South Pole or the North Pole. The polar vortex, it's a spinning for air, and it keeps the cold air locked in place. But when the vortex weakens, what happens when that top stuff starts to slow down? Starts to wobble, and starts to go around your table. Well, when that vortex starts to weaken, blobs of cold air are able to escape. And then that's what comes up. So we want the polar vortex. We do want it strong. We want it spinning strong to keep the cold air up there. It's when the polar vortex weakens is when blobs, you know, that top starts to walk around and starts moving around your tabletop. That's when you get those pockets of cold air, -30, coming out of the North Pole and dropping south. So we want a strong polar vortex to keep that, to keep it bottled up. Yes?
What causes it to weaken?
What causes the polar vortex to weaken? I'm not sure, but it's probably upper winds because the climate is changing now. upper level winds, we're seeing stuff that we've never seen before. Like even the computer models now, like I was talking earlier about the computer models, they would get data input. And there'd be normal data, normal range of data to be put in there. And then they would spit out numbers based on that data. But all of a sudden you're getting extreme numbers getting put in. And the computer says, oh, I don't know how to handle this number. It's out of my range, you know. So the computer models are even having difficulty with some of these numbers that are coming out now. So, yeah.
When that polar vortex weakens,
Yes.
and say pushes down into Florida or something.
Yeah.
Does some of the warm air get pushed back?
Yeah. So he was talking about the polar vortex when it weakens and it moves south. So as it pushes south, it'll dislodge some of the warm air north. And so now you got cold air going south, you got warm air going north. It's all chaotic. There's nothing normal about it anymore. So we want the polar vortex to be fairly strong to make things normal. Yes?
Speaking of warm, could you explain humidex to me and do you consider that an accurate weather observation?
Humidex. So what is humidex? Everybody's heard the term humidex before? So remember I was talking about sweating. When you have a relative humidity that's really high, so your body sweats. In order for it to sweat, it cools itself through evaporation. But if the water's not evaporating off your skin, that's because it's called a feel-like temperature. So the temperature should be 25, but because there's so much air, so much moisture in the air, your body thinks it's 30, 35, so it's not evaporating. It's the same thing with wind chill. Have you ever heard wind chill? Does anybody know what wind chill really means?
Don't go outside.
They've heard feel-like temperatures. So in the middle of winter, if you were just to stand outside and it was minus 30, you have a little pocket of air all around your body. It keeps you warm. It keeps you warm, a little bit warm. So at minus 20, you'd be so much. But if the wind blows, it blows that little pocket of air away. So your body has to make more. The stronger the wind, it has to make more. So the stronger the wind, it makes your body feel like it's minus 40 because it keeps having to make more and more and more. So the stronger the wind, the lower the wind chill. The reverse is humidex. So, about it?
Join me in thanking.
Just guys, I used to teach weather over in Moncton, New Brunswick for my job, and what I just did here would be about 3 months.